As an actuary, you'll be in charge of translating data into actual decisions for your executives and into risk-making rules for regulators. One important technique for deciphering data is regression analysis. In this course, ASRM 441, we'll be discussing linear regression and time series models. So we're going to start off with linear regression. With just 5 simple assumptions, we can make mathematical statements about how one variable affects the other. For example, let's say we're interested to determine how age affects insurance liability, which I'll call benefits. In general, we would expect a couple of things to emerge. First off, generally, if age increases, then benefits should increase. By benefits, I mean the amount of money that the insurance company pays. Some other things that we would be interested in determining is how much this increase is. For example, you can compare the insurance benefits for someone that's age 30 to someone who is age 40. And we expect that the 40-year-old on average would have a higher likelihood of receiving benefits, which would incur a higher cost for the insurance company. Other things that we care about, things like the likely range. What is the likely range for insurance benefits for a 30-year-old or a 40-year-old? Are they similar or are they going to be far apart? We also want to be able to report values of confidence, which means we're interested in determining what percentage of accuracy we are achieving and what sort of caveats do we have to include when we're reporting this to the executives, your manager, or your boss. All right, so now I'll start off by plotting out some points. Here's a plot with some points for individuals. On the x-axis, we have the individual's age, and on the y-axis, we have their insurance payout. How would you draw a line that goes through these points? Well, we could draw a line that goes through the first and last point, sort of like this. This technique is something that we will describe later on, called a random walk model. But for right now, there are some issues with this best fit line. It fits 3 points very well, but then there are 2 points that are pretty far away from the line, comparatively. So we want to adjust this a little bit so that it does a better job of fitting all the data points. We might choose a line that looks more like this. That sort of fits in between the data. Overall, there are a couple things that we want to focus on. First off, there should be approximately the same amount of points above and below the line. Alternatively, the distance above the line should be approximately equal to the distance below the line. So by that, what I mean is the distance from the actual point, if you drop straight down or go straight up until you hit the dotted line, or best fit line. So let me take away this bad line here. And describe this distance. we call this point here the error in using the line to estimate our y value. I'll include it for all our points. You can see it as the difference between the actual point and the best fit line, or our predicted value. So we have error equals actual minus predicted. We will notate this with an E for the error. The actual value is our actual y value. And our predicted value, we'll describe this in a couple of different ways. One way is with a y hat, where the hat on top indicates that this is a predicted value, not a real value. It's not from our data, but it's based off of the line that we created. We could also describe this using the actual equation of a line with a slope b0, an intercept b0 and a slope b1. This equation here, b0 plus b1x, is the equation of this line here, our best fit line. And so it's saying what y point corresponds to that x on the line, which gives us our error. Each one of these points has their own error, which we can indicate with a subscript. For example, I'll call this one E1 as a distance from this point to the line. Looking at this, is this error going to be positive or is it going to be negative? Well, if we go to our error equation, it's actual minus predicted. Our actual is below, and our predicted is a little bit larger. So this E1 is going to be less than 0. Over here, we have an E2, where the actual value is above the line, and so this E2 is going to be greater than 0. And one of our goals is going to be to make sure that this error is somewhat the same for all the points. So we don't have a bias towards any particular part of the graph. And we also want to make these errors as small as possible, because the smaller the error that we have, the more confident we can be about making predictions, as we'll see later on. So what we want to do is to find a way of combining all these errors together into a single formula, which we will call the sum of squared errors formula. What we do is we take our error, E, and we have a bunch of different points, so I'm going to index this. We want to square these errors. This has two purposes. First off, when we square the error, this negative error will, when squared, becomes positive, and so it won't cancel out with the positive error. We're also working with distances, and distances require a square of the difference, and so it's natural to use a squared error here when we're trying to minimize the distance to the line. But we don't want to focus on just one error, so we want to sum these all up. We'll start from the first observation until the nth observation to get the total sum of squares, which we will call SS, the sum of squares. It's not immediately obvious what this formula really is doing, so I'll expand it out like this. Of yi for a particular y minus b0 plus b1xi squared. And we're going to do this for every single observation. In this case, we have 5 points. This is going to be 5 of these squares that we add together. Now, this sum of squares function is based off of the x and y data, but it's actually not the parameters that we're focusing on. What we really want to focus on are these two parameters here, b0 and b1. They describe the line that we are working with. And so if we want to look at a different line, then we would have different b0s and b1s, which would get us different errors, and thus a different sum of squared errors. So it turns out that this function, the sum of squares function, is a function of b0 and b1. All right.